No, there are no tutorials in this semester. You're right, Ray. Okay, we'll wait 2 minutes and then we can start. Do you have received my mail regarding the additional lecture today?
Yes, yeah, I received it.
Perfect. Okay, it's 2:15. I think we can slowly start. Maybe some of your fellows will join us in the next minutes. Yeah, so welcome everybody on this rainy, stormy Wednesday afternoon. A perfect day to study microcomputer technology because going for a walk is also nice. And therefore, we are stay at home and try to understand the next steps. Yeah, good that you have received my notification via e-learning. Tomorrow I cannot offer a lecture because tomorrow and on Friday we have some applications for new profs here in Schweinfurt, for new robotic profs, and tomorrow and on Wednesday there are the Probelehrveranstaltungen, so sample lectures by the candidates, and therefore I cannot be in the Zoom session because I'm one member of the application committee and I have to review the candidates and to ask questions, and you know how an application may look like. Yeah, Professor Kaub is he's the head of the application committee, and therefore I think he will also be tomorrow, and on Friday he will be in the sample lectures. Okay, and of course you are also invited. So if you want to come, that's a public lecture, sample lecture, then you can get a first view on potential new profs, and yeah, the students are also asked for their opinion after the session. There is a speaker from the students, and there's a small session only with the students. Then you can say, oh, good candidate or not so good, or whatever you have recognized during the lectures. It's tomorrow. I'm not sure the lecture room. I'm not sure where it is. It must be a very big one to keep distance, and I'm not sure if there is not a restriction regarding the people in the room. That's possible tomorrow because due to Corona and the current situation. But in general, such applications are public ones, so you can attend and can tell your opinion. Okay, so back to our chapter subsection 4.1. We have talked in the last week about some characteristics, how we can design a microcomputer, a microprocessor, and we have stopped here with Flint's taxonomy. That's another distinction of microprocessors based on their parallelism in data processing. So parallel or concurrent processing of data. and this is a 2 times 2 matrix. On the rows, we distinguish between single data that is processed and multiple data that is processed. And on the columns, we distinguish between a single instruction is executed or multiple instructions are executed within one step. And now if we combine 2 times 2 different characteristics, then we can see 4 different abbreviations, SISTI, SIMDI, MISTI, and MIMDI. So we can distinguish between single instruction, single data, single instruction with multiple data, multiple instructions with single data, and multiple instructions with multiple data. And examples for this classification is shown here on this slide. So the traditional way how information can be processed is SISTI, single instruction, single data. So you have one single processor, one single CPU, and you process with this one single CPU, one instruction per, for example, clock cycle, and the instruction is performed exactly at one piece of data. Yeah? So only one instruction per time, and each instruction is used to process or to transform one input data. That's the traditional way, and that's how we have studied the microprocessors up to now, and we will also define our own microprocessor exactly in this way, SISTI. Then the next classification is SIMDI, single instruction, multiple data. So one instruction is executed on multiple data in parallel. So this is, or the easiest example how you can imagine this, if you multiply a vector with a constant value, and you have to multiply each component of the vector with this constant value, then you apply the multiplication, so one instruction, a single instruction, to multiple data, because the components of your vector are the multiple data items that are processed in the same way, but only with one instruction. And here are additional examples. High performance computers work in this way. So for example, vector computers or array processors, or oftentimes graphics applications. So for example, also computer games are executed in this way, and there are several libraries that can be used to realize SIMD processing. For example, MMX, multimedia extension, that's a library from Microsoft. 3D Now, SSE, streaming SIMD extensions. So these are all examples for the parallel processing of multiple data items by one single instruction. GPUs, graphic processing units, work exactly in this way, or DSPs, digital signal processors. So you process several input signals in parallel with the same operation. The taxonomy, Flint's taxonomy, is very old, to be honest, published in 1966, but also nowadays this classification is used. And the two remaining characterizations are shown on the next page. With MISTI, multiple instruction, single data, you use several instructions, several commands, and execute them in parallel on one piece of data. And up to now, there is no practical application for MISTI, probably in fault tolerance systems. So if you want to define, for example, a safety circuit, a safety processor that monitors, for example, a plant, a nuclear power plant, then for such fault tolerance systems, there are theoretical applications of MISTI, but very less real-world applications. That's MISTI is there because we have 2x2 different combinations, and you see here are some brackets around MISTI because there is no good application example for this. But for MIMDI, multiple instruction on multiple data, there are some real-world applications. So, for example, if you have an independent parallel data processing, so you have several instructions that are executed in parallel on different or a set of data items. And this can be found in mainframes, supercomputers, or in a multi-core system. So your desktop PC also supports several processing cores. So Intel processors offer in general 4, 8, 16 processing cores, and within each core you have several threading cores, and here you can use MIMDI to execute different commands in parallel on different CPUs. Multi-threading is also an example for MIMDI in a single core system. So if you implement, for example, a thread in Java or in Python, and this thread is dispatched to your single core for a specific time, and then another thread is executed, and then another thread, and so on. So you have a round robin between the threads. This can be also seen as MIMDI, or if you have a GPU with several thousand cores to process your graphical data, for example, for your 3D ego shooter, if you want to play. So this classification is still in use, but nowadays the standard way, conventional way, is SysD, and for graphical applications, SIMD or MIMDI. That's Flint's taxonomy, and then we have another term that we have to know, so-called RISC architecture and the CISC architecture. RISC stands for Reduced Instruction Set. So you have a very small, compact, reduced instruction set, and this is tailored for energy saving and a very fast architecture. So you use mostly constant instruction length in your memory. You can remember an instruction can be expressed with 1 byte, 2 byte, 3 byte, depending on how complex is this instruction. And for a RISC architecture, we oftentimes see a constant instruction length in memory, and also pipelining is possible. That means we can overlap the fetching, the interpretation, and the execution phase. We will see the details later on, but you can remember one instruction can be divided into a fetch phase, where we first read the instruction, then make an interpretation to know which instruction should be executed. Then we fetch again the necessary operands, and then we execute everything. And if you have a RISC architecture, then you can also pipeline this. That means during or in parallel to the fetching phase of one command, also the interpretation of the previous command is done. Therefore, you can save time because you overlap the different phases that are required to interpret and execute a command. As example, we have our ARM architecture, highly optimized for energy saving, or we have PIC microchip, and there are different other examples where RISC is used. So if the instruction set is boiled down to a minimal set, then we talk about RISC architecture. A CISC architecture is exactly the opposite. Here we have a complex instruction set, computer, and A complex instruction set means that we have variable instruction length, and we have a lot of commands, a lot of sophisticated commands, and therefore the programming is simplified because we can use one command on a CISC architecture, where on RISC architecture we need 2, 3, or 5 commands to express the same behavior or to describe the same functionality. So on CISC, the programs gets more compact, but in the end, the architecture must be must offer more functionality to work with this instruction set. And yeah, classically the x86 instruction set or the AMD instruction set, that's an example for a CISC architecture. So the classic desktop PC with an Intel processor or with an AMD processor. Some of you prefer AMD. We have already discussed this. Some of you prefer Intel. These are classical examples for CISC architectures. So your programs, if you want to work with assembler, your programs gets very compact because the architecture is very sophisticated, but not optimized for power consumption, not optimized for processing speed. So in the end, the CISC architecture is a better idea for mobile devices. So in your smartphones, you will find ARM architectures, so you find RISC architecture, and in your desktop PC, you find CISC, but nowadays there are nearly no real desktop PCs anymore. Most of you use a laptop, a notebook, and for notebooks, a RISC architecture is the better decision. Okay, so that's all regarding the characteristics. Are there questions before we go ahead?
Yes, I have a question to the previous concept of multiple instructions and multiple data. You said that, yeah, this concept, but you said that usually now we use SIST, SIST. And but what about our computers which we are using these days? Are they not MIMD, like MIMD?
Yeah, you're right. Your standard desktop PC supports MIMD because you have multi-threading. If you have only one core, you can use multi-threading, but in general, you have several cores in your desktop PC. So the standard way for it, or the standard mode for a desktop PC is MIMD. And SIST, we will see that in a few minutes that for our own microprocessor, we start with SIST because to design and to implement the processor, the first step is to realize SIST. And then if you multiply the processing cores, you can easily move from SIST to MIMD because they are the two edges of one scope. Here SIST on the left side, MIMD is on the right side, and all others are in between. So now for the construction, we use the SIST approach, but your real-world PC offers you MIMD. That's correct.
And are they fixed to a processor? Like, for example, is a processor fixed to SIST or MIMD, or can they also change between them?
No, they in reality they oftentimes support several of these modes. So if you take a look at one core, this one core can be designed in a way that it works in a SIST way, but the combination of several cores within one CPU, then the overall functionality is MIMD again. So you cannot switch, you cannot say, I want to switch between SIST mode or MIMD mode. That's an architectural approach. So that's during the design phase, of your CPU, you have to decide should it support SysD or MIMD. But oftentimes on different levels, different modes are supported. So on the level of one core, there is SysD, but if you integrate several cores into one unit, then you have MIMD.
Yeah, understood. Thank you.
Is SIMD more powerful or MIMD? Yeah, SIMD is, in the end, you have only one instruction. So in the easiest way, for example, an addition plus, and you execute the plus on several data items in parallel. So you can add, for example, 3 pairs of digits. Then you have SIMD. And with MIMD, you can say, I want to execute an addition, a subtraction, and a multiplication in parallel, and each operation in parallel on several data items. So MIMD is more powerful. It depends on the definition of powerful, of course, but I guess you mean how fast or how versatile can the calculation be? And MIMD offers you the most flexibility. Yeah? So you can execute different commands, plus, minus, multiplication, division, on several data items in parallel. Yeah, how fast also depends, of course, how the CPU core is designed. So if we have enough time, we will also see some optimizations that are used in the real world. So for example, that we have pipelining of commands. I've already mentioned this. Or for example, modern CPUs have functionality like branch prediction. I'm not sure, but I think I've already mentioned branch prediction. So if you have your assembler code and you reach a branch, so branch BLE or BL0 or something like this, and then your CU, your control unit, tries to predict what is the result with the highest probability. And then it executes ahead already these commands. And if the prediction was correct, then you save time. If the prediction was false, then you skip the result. So branch prediction is a very complex, but also very performed way to enhance the speed of your system. And there are several such approaches that pays into speed, computing speed. SysD faster, MIMD versatile, right? SysD less complex in the design of the CPU, MIMD versatile, and of course faster because I can execute, for example, if I've got 3 instructions and I use SysD, I have to execute them one after another. In MIMD, I can execute the 3 instructions in parallel and also using several data items. So you can think of MIMD as multiple times SysD. Maybe that's the easiest explanation. Okay. Good. Then we take a look at our own microprocessor. This is my favorite subsection here. I have mentioned this several times because we now try to invent and design our own 4-bit processor. And what we need beforehand, before you start with a new product, is always a good logo. You need a good branding. You need a good eye catcher that you can get your customer. So you are my customer now, right? I want to sell you our 4-bit processor, And therefore, I introduce this logo here on the right side. The IC, the microchip with FHVS on it as printing. And if you see this logo on the next pages, you always know that we want to realize a specific approach for our own microprocessor. Yeah. So first the commercials, and then in the end the product, like in the real world. So here is our logo, and here are some characteristics that we want to apply now, that we want to implement. We will see that we have now repetitions from the previous slides and from the last week. We start with the instruction size. The instruction size in our system will be 8-bit, and the data size will be 4-bit. Therefore, we have a 4-bit microprocessor because the address bus and in the end the data size takes 4 bits, and an instruction is encoded with 8 bits. So in the end, we can encode 2 power 8, 256 different instructions, but we will see later on, we will only use a subset of all these combinations. But in general, 8 bits per instruction, 4 bits per data item. We will only implement 2 registers, A and B. So we follow the classic approach. We have an accumulator and an additional register to execute our operations. So you can, for example, imagine this as an addition. For an addition, we need 2 summons. The first summon in register A, the second summon in register B, and then we can execute our addition. We only have 2 status flags, a set flag, a 0 flag, and a C flag, a carry flag. So we have no flags for overflow, we have no flags for negative or something like this, like in the previous chapter. We only have set, 0 flag and carry flag, and you will see that's sufficient. That's enough. We can solve all problems only with these 2 flags. We must be able to recognize 0, and we must be able to recognize a carry if we have executed, for example, an addition, and the operands are too big for our registers. We have a maximum of 64 KB of instruction memory, and we have a data memory with 16 words. Each each data item has 4 bits, so therefore we have 16 times 4 bits to store our data. So the data memory is very restricted. We have only 16 positions. So if you want to write a program that handles more data items, then you have in the end a technical problem, because you have not more space to swap your registers to your data memory. We have only 16 slots, not more. And here at the bottom, we have our instruction set. You see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18. We have 18 instructions. Here, BX, there are different types of the branch we will see on the next slide. So we have round about 25 instructions, not more. Yeah? Not more. And if you compare this with our ARM instruction set from the last weeks, you can see that this instruction set is really, really reduced to a minimum that we need. So what we can state now in our mnemonic code, we can load a register A or B with a constant or a memory cell. This is stated with LDX, and you have to replace the X with A or B. So there is a command LDA for load register A, and there is a command LDB for load register B. On the next page there is a table with all commands. So I give you the overview here, and then we take a look at the details. And we have a command to store register A or B to memory. Therefore, we use STA or STB. And we have some logical operations on A and B. So we have logical AND, logical OR, logical XOR, and inversion, bitwise inversion. Then we have increment or decrement of register A, like in C++. We have INC and DAC. We have shift operations. And the shift operations always work on register A. So register A is the main register, the accumulator, and most of the operations are only possible on register A. So you have to move register B to register A first if your operand is in register B. So SFTR means shift to the right of register A. SFTL means shift to the left of register A. Then we have rotation commands with rotation to the right with carry and rotation to the left with carry. We can make a rotation of the bits in our accumulator to the left or to the right using or skipping the carry flag. And the difference between shifting and rotating is that with shifting, you move out the bit patterns. So if you shift to the left, from the right side, you push in zeros and the bits on the left side will disappear. And with rotation, you move the bits out at the left side and move them in on the right side, like a circle. So rotating is a circle operation in the end. Shifting is moving out, shifting out to the left or to the right, and rotation means move the content like a circle in the register. Then we can add or subtract. There is no multiplication here. We will see how to implement also multiplications. There is no division here, only addition and subtraction with add and sub. And we have two operations to set and clear the carry. CLRC means clear carry. SetC means set carry. Sometimes it's necessary that we store a defined value in our carry flag, and for this purpose we have clear carry and set carry. Then we have C2set. With this command, we can transfer the carry to the 0 flag. So if we need to know, okay, what's in our carry, we can move it to the 0 flag. Sometimes that's interesting. And we have free branch instructions, BX. And the free instructions are simply branch without condition, branch for a 0. So this will be executed if the 0 flag is 1. And branch no 0, that means this will be executed if the 0 flag is 0. So if there is no 0. And because we have no branching for a carry, we can use C2set, copy carry to 0 flag, if we want to check for a carry. So if we want to check for a carry, we first invoke C2set. And then we can use the B command, bset or bnset, to check for the content of the carry. Okay. Questions? No? Okay, then we take a look how we can realize this. Our 4-bit processor will use a Harvard architecture. You can also see this on the main slide here on the top. Why is this in Harvard architecture? Where is the hint that this must be a Harvard architecture?
2 different memories.
Exactly. We have an instruction memory and we have a data memory. And with 2 distinct memory blocks, we say, okay, this is so-called Harvard architecture. Yeah, now we go step by step to each function block in our CPU and first outline the overall functionality, how it should work, and then we show how it works here in our own implementation. Okay, so let's start with our ALU, our arithmetic logic unit. Here on the right side, you see again the block. Oh, sorry, wrong cursor again. Here on the right side, you see again the block diagram for our CPU. That was our starting point at the beginning of the semester, right? And now we go through the different components here and try to outline what's necessary to realize this and how we have done it here in this special use case. And we start with the ALU, with the arithmetic logic unit. For the ALU, we need some basic logic operations and we need some basic arithmetic operations. As logical operations, in the end, it's sufficient to implement AND, OR, and NOT. Why is AND, OR, and NOT sufficient? Can you remember this from the beginning of the class?
Because these are the basic logical operations using which we can perform any other logical operation.
Correct. And how do we call this? This set of the minimal set of operations? Starts with B.
Basic or base operation?
No, that's bool base or Boolean base.
Bool base. Boolean base.
That's a bool base. So AND, OR, and NOT, that's one minimal set. And we can, you have explained correctly, we can use AND, OR, and NOT to realize everything else. And we have exactly started in this way. We have first defined AND, OR, NOT, and then we have built on these basic components and we have constructed everything else. So if we know how to execute AND, OR, NOT, then everything is perfect because that's enough. But to simplify our sampler code, we also add an additional XOR. You will see that XOR, exclusive OR, simplifies all our programs, but you also know that XOR, that's in the end A and not B, or A and B bar, or A bar and B. So you can also define XOR with the 3 others. But we offer it as one component, as a black box. Yeah, then we need an addition and a subtraction of integer values. And we give or we define some shifting operations and some bit rotations. Shifting and bit rotation are also convenience instructions. If we have addition and or not, then we can solve everything. But subtraction is nice to save some word. XOR is nice, and also shift and rotation is nice to save some work. Okay, if we have a modern CISC architecture, we can also do more complex operations. For example, multiplication, division. We can work with floating point numbers with different accuracies. We can also calculate some trigonometric functions or we can use vectors. So in a SIMD system, we can also add, for example, directly vectors with several components. So this is for real-world CISC architectures. Our own processor only supports this very basic instructions here at the top. Okay. Then we'll take a look at the next slide. And here on slide 67, we can see the basic structure of an ALU. So how, in general, an ALU is designed. The common way to design an ALU is to use two registers. I mark it here, two registers, for example, A and B. And these registers are, in the end, memory locations, or you can also call them variables to store the operands that I want to use for the next operation. So in this example here, we want to calculate the sum of two sums. Therefore, we store sum 1 in register A and sum 2 in register B. And then we throw both operands to our ALU. The ALU will execute the addition and will write the sum back to another register. Here we have 3 registers, 2 for the operands, 1 for the result. Oftentimes, to save money, the third register is omitted and the result is written back to one of the input registers. So I, for example, add 3 plus 5, that gives me an 8, and the 8 is written back and overrides the 3. That's again an optimization, but the most general way is we have 2 registers for the operands, 1 register for the result. And the block symbol, the diagram symbol for the ALU looks like this. How does it look like? Like a V, or so it looks like this. This is, so to say, the standardized symbol for an ALU, like a spaceship again, or like a V. And the idea is we have 2 input channels for our operands, 3, 5. We execute, for example, a plus, and here at the bottom, we get our result 8. Okay. So what's the full form? Is 6. What do you mean with 6? Do you mean this complex instruction set computer? CISC and RISC, or what do you mean? CISC, yeah, that's a complex instruction set computer. So that was shown here on slide. Which slide? This slide. CISC, complex instruction set computer. Okay. So back to our ALU. So whenever you see this little weird symbol here in a block diagram, think of an ALU. You can execute arithmetic and logic operations. Okay. So the ALU offers different operations, right? Addition, subtraction, maybe multiplication, logical AND, logical OR. So we have to switch our ALU before we start with the operation to a specific mode of operation. We have to define, oh, I want to execute a plus, I want to execute a minus. And this is done via several control lines. Here we have 4 control lines. So in this special case, we support 2 power 4. So we support 16 different logical and or arithmetic operations, because we have 4 bits to encode our instruction. So the control signals are used to determine, okay, what should be executed, plus, minus, whatever. And after the result has been calculated and written back to the output register, the ALU also updates our flags. The flags are stored in a special register, in the status register. The status register can only be read by the ALU, and read and can only be written by the CPU. Can only be written by the ALU. But you, as a programmer, you know that you can read the status register. You can check for 0. You can check for sign. You can check for carry. You can check for overflow. So updating or writing the status register is done by the ALU. Reading and interpreting the status register is done by you as a programmer. Questions? Okay, then I've got a question. If you have, for example, an instruction like this in your C++ code, I write it here, 3 plus 5 plus 6. How is this instruction executed within your CPU, or to be more precise, within your ALU? Your ALU only has 2 inputs and 1 output register. How is this command interpreted? What is done behind the curtain?
3 plus 5 would be saved back to register A, for example, and then plus 6, the result into register B. Or, you get what I'm saying?
Yeah, I got it. So you've said first 3 plus 5. And yeah, Rehan, you've written the same. And then the result of 3 plus 5 is an 8, is written back maybe to a result register or again to register A, and then plus 6. And this is done by your compiler in the end. So if you write a very complex statement, your compiler makes interpretation, and the compiler always starts with the operators. So the compiler, there are several components in your compiler. There is a tokenizer, and there is a component that interprets the single tokens and makes an execution. And the first step is to search for the operator. Here the operator we have 2 times plus. So plus is the same operator. So there is no priority between the operators. And therefore it starts from left to right. And then it recognizes the first plus. And then it looks to the left and to the right side. And on the left side, it can identify a literal number. So it moves the 3 to register A. And on the right side, it also sees a literal number. So it moves the 5 to register B, executes a plus. So the control signals are signaling a plus. And then the 8 is written to register F or directly back to register A. And then this boils down to 8 plus 6, and now it fits into your ALU. Now it executes this command with 2 operands. And this interpretation of your statement, this is done by your compiler, and the compiler brings this to assembler code, and the assembler code is interpreted by your ALU. And if you mix, for example, 8 plus 3 times 4, then you know in your programming language there is something like a priority of the operators. So like in math, the multiplication will be executed first, and after the multiplication, the addition. But if you want to change the sequence of the interpretation, you can work also with some brackets. Yeah? So this interpretation is done by your compiler, and then you will see that complex statements in C will be executed step by step in smaller parts by your ALU. If we don't have a multiplication, how can the ALU execute this? We don't have
Doing it 4 times.
Once again, please.
By doing it 4 times.
Yeah.
This addition 4 times.
Yeah. So a multiplication is a shortcut for an addition, right? So we have to write 8 plus 3 plus 8 plus 3 plus 8 plus 3 plus 8 plus 3. And then we have replaced the multiplication with an addition, and then we can execute it again. So we don't need a multiplication. We don't need a division. You can everything express only with plus, with addition. And we also know that subtraction means if you write, for example, 5 minus 2, that's equivalent to 5 plus minus 2, and minus 2 is 2's complement of 2. So in the end, we only need an addition and an inversion, a 2's complement, and that's enough. Yeah. And this is the job of your compiler and of your compiler that produces your assembly code to decompose to the easiest instructions that can be interpreted by your ALU.
You also once mentioned that multiplication or division, I'm not sure about these both, they are also carried by shifting bits.
Yeah.
So is that, was it multiplication or division?
Both.
Oh, both. Wow.
Multiplication is shifting to the left, and division is shifting to the right.
Oh, okay. So very easy. So so indirectly we do have multiplication and division then in our processor, in our CPU.
Yeah, you can mimic it by other operations. So why we do it like this? For the programmer, it's easier if there is a multiplication, a division, whatever, of course. But if you are the system engineer at Intel or at Apple and you have to design the CPU, then you want to design a CPU that offers high performance. But for you as the system engineer, you have to design a CPU that is very, very cheap. Because you want to earn a lot of money, and if your system is so complex that it takes a lot of money, then you have no return on invest. Yeah? So therefore, you want to make it as easy as possible. Of course, you can add a lot of instructions for the convenience of the developer, but then your CPU becomes more and more expensive. That's not your mission. Yeah? Hope the expression is commutative, you mean? Yeah. So sometimes some expressions are commutative, some not. Yeah? Division is not commutative. So if you have to take the sequence into account, you must be careful, right? You cannot switch the sequence of the operators or of the operands. Okay, so this is our general layout for the ALU, and now we have to realize this. Now it becomes more interesting because we have to offer an appropriate ALU for our 4-bit system. And now we have to understand why is this an ALU? Okay, where to start? Let's start here at the top. Here at the top, you see our 2 working registers. we have only two working registers, A and B. Both takes 4-bit. We enumerate the bits with A0, A1, A2, A3, respectively B0, B1, B2, B3. Okay. So now we want to realize an addition, because the easiest way, or the only operation that we need in the end, is an addition. We have seen on the previous slide, you can reduce everything to an addition. Therefore, we want to offer an addition and an inversion. We need addition and inversion, and therefore we do the following trick. Okay, we need one ALU, but we can simply decompose the ALU into 4 1-bit ALUs. So for example, if I want to add 1, 0, 1, 1, and 1, 1, 0, 0, this is register A, this is register B, then we can say, okay, I execute my addition based on the positions of the bits within my registers. So if I've got a 4-bit register, I need 4 times the 1-bit ALU to execute the overall logic or arithmetic operations. And this is shown here. We have 1, 2, 3, 4 blocks. Each block represents a 1-bit ALU. Each block takes exactly 2 inputs from the register A, one from the register A, one from the register B. And you can see here that on the right side, I connect A0 and B0. Now maybe you take a note and it becomes clearer here. In the next one, I connect A1, B1, A2, B2, A3, B3. So these ALUs execute the operation for exactly one position, only for one position. But it's possible that from the previous operation, there is a carry. So for example, if I add 2 4-bit numbers, and here at the leftmost position, I've got 0 plus 0, then I get 0 carry 1. And this carry that is produced here must be fed to our ALU. We cannot skip it, we need it. And this is added here at the right side. We have the C in, this carry in. This is the carry from the previous operation. This is connected here at the rightmost position. And now the idea is, if, for example, I want to execute an addition, then I use my control lines here, C0 to C6, and switch all these components to addition, and then the first 1-bit ALU adds the first 2 bits of both registers, produces a result, and this result is given as the carry to the next 1-bit ALU. And this 1-bit ALU adds the next 2 bits plus the carry, and it moves or gives the carry to the next position. In this block, I add A2, B2, and the carry from the previous position. And then at the last position, I add A3, B3 plus the carry. And this produces maybe a carry over, a CO, to the next operation. That's the C out for the next operation. That will be the C in the next iteration. Okay. So this is how the single 1-bit ALUs work. I take a specific position of my registers, execute the operation, and give the carry, if there is one, to the next position, and so on. Here, are my control lines, C0 to C6. So here at the bottom, I've got 6 1-bit lines. Here is only one line that represents the bus to save some space. But here I've got 6 lines, and with this 6 lines, 7 lines, C0 to C6, 7 lines, and with this 7 lines, I can select one operation out of my available operations. So this ALU will support different operations, and I select one operation by a specific bit pattern on this bus. I will show you the bit patterns in a second. And then, last but not least, we have here 1, 2, 3, 4 outputs are. These outputs are used to create or to calculate the status for our control flags. So, for example, if I want to calculate the 0 flag, then I use a NOR combination of all outputs R0 to R3. Why NOR? Why a NOR? Because a NOR only produces a 1 for the input combination 0, 0, 0, 0. This will produce a 1. So if within all 1-bit ALUs I have stored a 0 and I've copied this value to this intermediate register, and I combine 4 times a 0 with a NOR gate, this will produce a 1 at the 0 flag. And that's what I want to check. I check if in my ALU all positions are 0. If all positions are 0, then I have to set a 0 flag, because all position 0 means I've got a 0. For all other combinations, this will produce a 0 here, the NOR gate. So this sub-circuit here produces the 0 flag. Of course, I need some circuit to indicate, for example, negative if I want it, or carry, and so on. But we have seen on the first slide, we only have 2 flags, 0 and carry, nothing else. The carry can be read here. This is our carry in the end. And the 0 flag is constructed here. Okay, questions? No questions? Okay. Then we go ahead. We need to know, okay, how does the 1-bit ALU look like? This is simply a rectangle in a block diagram. That rectangle has no functionality. We need to know what's inside this black box. How does it work? And for this purpose, we take a look at the next page, and we try to understand how the 1-bit ALU work. So, and here, the next page, you see the logic circuit for one 1-bit ALU of the previous slide. So this is one of the black boxes on the previous slide, and this is our 1-bit ALU that processes one position in our number. Okay, now we have to understand what's going on here. Where to start? Let's start with the multiplexer here on the right side. The multiplexer. You can see here on the right side we have an OR gate that produces our result. And we have here 4 times an AND gate. And one input of each AND gate is connected to the control lines. Let me zoom in a little bit. It becomes easier to read. Yeah, that's better. One input of the AND gate is connected to the control lines C3, C4, C5, C6. These control lines are used to select one operation, exactly one, out of summation, logical AND, logical OR, or logical XOR. So that means if I, for example, put a 1 here, then I select logical OR. So if I use this bit pattern to make it complete, then I select logical OR. Why? Because then this AND gate becomes conductive, right? So the output of this AND gate only depends on the second input. But the second input, you can see here, this is an OR gate, logical OR, of our inputs A and B. Here are the inputs. These are the bit positions of the registers A and B. So if I use the bit pattern 0010, I enable this AND gate. This AND gate uses the output of the OR. The same works for XOR. So if we want to enable XOR, what I have to write here on the left side, if I want to execute
0001.
Exactly, I have to write 0001. That means the 3 upper ANDs will produce, of course, a 0 because one input is 0. But the lower AND here, this AND, is enabled because I've got 1 here. So the output only depends on the second input, and the second input is the result of XOR. Here's our XOR, and I've connected the XOR with A and B. And this is a multiplexer, right? We have seen a multiplexer in the first semester, because using these control lines, I can select 1 out of 4 operations. 1 out of 4 operations, and the OR is simply the connection of 1 out of these 4 AND gates. So this will produce our result depending on the selected operation. And we have a way XOR, OR, and AND. These are the operations that we have that we have defined in the beginning that we want to support, AND, OR, and XOR. Okay, but that's not enough, right? We need additional operations, and what we have to do is shown here on the right side. Let's see, maybe it works like this. So let us see if we can find the different combinations again. A and B. For A and B, we need the bit combination 0100. That's what we have done beforehand, right? For 0100, we enable logical AND, and the control lines C0, C1, C2 are simply ignored because the upper part of the circuit is disconnected from the result because the multiplexer selects the XOR. If we want to enable logical OR, we need bit combination 0010. For an XOR, we need 0001. Yeah, Adam has said this, I think so. For a not A, let's see what's a not A. and not A is 1, 0, 0, 0. And now we also need the other input lines, the other control, C0 to C2. So if we enable the sum, here, that means we disconnect the lower parts and we only have to take the upper part into account of our circuit. And we use C0 with a 0, C1 with a 1, C2 with a 0. Then I got the combination 0, 1, 0 here. And now we have to check what's going on here. In the upper half, we have a full adder. And in front of the full adder, we have two XORs. One XOR takes input A and control line 1. The lower XOR takes B and control line 0 and control line 2. And for this combination now, if we have 0, 0, 1, 0, so we have C in, this is also 0 here, the carry is 0, and we have the bit combination 0, 1, 0. This will produce us a NOT. This will produce us a NOT end. So an inversion of our register A. Because for this combination, 0, 0, 1, 0, we've got a 0 at the carry, at the full adder. We have our input from the register A. We have the line C1 is 1. So C1 is 1. That means if A is a 0, it will produce a 1. If A is a 1, it will produce a 0. So this XOR will produce exactly the opposite of the available bit in the register A. And B, let's check what's going on for B. For B, I combine B with C0, but C0 is 0. So this AND will produce a 0, only zeros here. And this XOR here, we have 0, XOR 0. This will produce also a 0. So I'm adding our inverted register A plus 0. So I've got not A. This is not A. And yeah, now we can check all the columns. We do one additional and the remaining ones are as a small homework for you. For example, we want to execute an addition, A plus B. If we want to execute an addition, we have to switch our circuit to summation. This is done here at the bottom. I use A plus B. So we select summation. We have here at the bottom 1, 0, 0, 0. That means the lower part of the circuit is deactivated. We have only to take into account our full adder. And for the full adder, we have input combination 0, 1, 0, 0. That means what happens now in the end? We use A XOR C1, no, A XOR C1, yeah. So this will, if A is 0, then I've got a 0, it will produce a 0. If A is 1, this will produce a 1. So we simply take our register A as it is. And then we combine this in the full adder with B. B is XOR of B and C0. C0 is 1, so we simply enable B. We have B XOR 0, so this is again a B. And then we make an addition, a full addition of A and B plus C in from the previous position. So this is plus 0, so we simply make a summation. And this summation will produce a 1 or a 0, and in special cases, a carry over to the next 1 bit ALE. Okay. What were the C0, C6 outputs? No, C0 to C6 are not outputs, they are inputs. These are the control lines to select an operation. So for a specific input combination, a bit pattern on C0 to C6, I switch this circuit, for example, to logical AND, or I switch it to logical OR, or I switch it to addition. So these control lines, the signals on the control lines are defined by your source code. If you write A plus B, then the control lines are set to the pattern for plus. If you write inversion A, then you switch the control lines to bitwise inversion of register A. By which component? Which component creates the signals on the control lines?
Control unit?
Huh?
Control unit? CU?
Yeah, the CU, exactly. The CU, the control unit, exactly. Yeah, the control unit fetches your code, interprets your code, recognizes, oh, he wants to make an addition, and then it creates the corresponding control signals on the control lines. So everything starts with the inputs, with the control inputs. Again, it depends on the construction of the control unit. You can, for example, first provide operand A, then provide operand B, then create the control signals and then execute. Or you can first enable the operation, then prepare operand A, operand B, and then execute. That's depending on the internal construction of the CU. But we will do this, maybe not today, but in the next week. Okay. Here are two ones specially marked for you for the subtraction. The subtraction is, of course, done based on the 2's complement. So if I want to execute A minus B, this is realized as A plus minus B, and minus B is created with a 1 at Cin, so at this line Ci here, and A plus B, and A minus B, the bitwise inversion for the 2's complement is realized with a 1 at the command, the control line C2. So the most complex one is A minus B, because we have to realize this with 2's complement. And for 2's complement, we need bitwise inversion, and we need +1. And therefore, we need 2 1s at Cin and C2. Okay. Yeah, and that's it. So this circuit can be found within each of these blocks here 4 times. And each block produces 1 bit for the result. The result is stored in another register or directly again at the input. And based on this output register, at the result register, I can, for example, derive the symmetry. This is not shown here. So the derivation of the 0 flag is not shown here. This is only the functionality within one of these boxes. And as a short repetition, if you cannot remember how a full adder works, it's shown here at the bottom. A full adder is constructed out of two half adders in series in combination with a XOR. Because for a full adder, I must be able to add 2 bits, and I need to add a carry from a previous position. So a full adder always adds 3 bits. For the bits A and B, I use a half adder. Then I use the result of this addition and add this with the carry. This produces the sum, and eventually there is another carry that is produced via this OR gate here. So this is content of the first semester. We have studied this in the first semester, so you can go back if you have forgot the details. Then you can go back and take a look. Okay, and that's it. That's our ALU. Questions? Okay, then to get familiar with this circuit as a small homework, to try to figure out how the remaining columns here in this table work. Yeah? So select a specific column, switch this circuit to a specific mode of operation, and try to figure out if the result is really, for example, an increment or a decrement or whatever. Okay, now we've got an ALU, very good. And yeah, now we have to realize this. We have to do a technical realization. And this looks very complicated, right? And the good news is that we skip these details. Why? Because this CPU only exists as a simulation in a hardware description language. And the most widely used hardware description language nowadays is VHDL. VHDL is a programming language that you can use to define technical components and to execute these technical components within a simulation. And on this slide, you see the complete implementation of this ALU. And the code, the syntax that you can see here, that's VHDL. And VHDL is not part of this lecture. This is simply a hard copy from another class, a class not by me, by Heinz Endres. And he's the real VHDL expert. And he gives a class, I think only a German class, I'm not sure, but I think it's only in German, where he explains how to implement in VHDL. So this is the direct implementation of this circuit. And if you compare it line by line, you will find a lot of similarities between the two approaches. So for example, here in the beginning, we define our inputs and our outputs that are used by this entity, by the ALU. So we have A and B as an in marks an input. We talk about unsigned bits, 4 bits. We have, for example, an output register that is defined by 4 bits, unsigned bits, and so on. So we will find all operations and all representations from the top here in VHDL. But we don't talk about the details. If you're interested, you can read it and you will very easily figure out, okay, how is the representation of the subtraction? The subtraction is implemented here. This is the subtraction. And if you're interested in the details, I recommend you that you always take part at the VHDL class from Heinz, but I will not ask you this in the lecture. That's too much. So you can take a small note, not relevant for the exam, but the parts in between are relevant. So on the next slide, there is an example how we can realize a hardware multiplicator. The problem is our system up to now only supports addition and subtraction, but addition is the base of addition. The question is there a way to realize a multiplication very fast, very efficient, completely in hardware? And there is one approach, you can find it in the book from Maltz, Rechnerarchitektur or computer architecture. And before we take a look at the circuit, we take a look at the multiplication and how we do it by hand. Then it becomes clear how the circuit works. So we want to multiply 9 times 7. That's 63 in decimal. In binary, we have to convert 9 to 1001 and 7 to 0111. And now, I hope you can remember this from the first part of the class. We simply copy the left operand for all positions where we have a 1 here. 0 times this is 0. 1 times this is 1001. 1 times this is 1001, and so on. So we simply have to copy the first operand, but we have to make a left shift. Can you see here the space, the gap on the right side? This is the left shift that is introduced by the different positions of the ones in the second factor. So I have to left shift the first operand, and then I add each column. So I add this column, this is 1, then I add this column, this is 1, then I add this column, this is 1, and so on. It's the same like you do it in the decimal system, but here it's much easier because you can only have 0 times or 1 times. 0 times you can skip, 1 times you simply have to copy. And here is the general approach at the bottom. If we have A0, A1, A2, A3 times B0, B1, B2, B3, then we have B3 times all of these bits, left shift 3 positions, B2 times all bits of the first number, left shift 2 positions. So here we have 3 positions, here we have 2 positions. Then we have B1 times all positions of the first number, left shift 1 position, and then we have simply B0 times all digits of the first number, no left shift. And then we make an addition again, and the addition is done, as we know, column by column. So we add this one, we add this one, and so on. This is how we execute it in with pen and paper. And we can also do this, of course, in a circuit. And the circuit is shown here at the top. We need half adders and full adders. The full adder has an additional input here. It's labeled with ÜE. That's German for carry. In German we say Übertrag, and therefore we have ÜE, Übertrag, carry, for the full adder, and for the half adder we have only A and B. And now if we want to multiply 7 times 13, then we have the 7 here, as operand A. We have the 13 here as operand B. I tried to mark it for you. Here is A, here is B. And now we do exactly what we have done in our manual approach. We make, or we use the half adder to produce the sum for the first digit. We simply use an AND. This is the first position, and this produces the output. Here on the right side is the output for the result. This produces the first position, and we also use the first result left shifted, and this is shown by the diagonal lines here, to the next computation. And in the next computation, we use a full adder that adds the current bits, so the current position, plus the shift from the previous position. And it's repeated for the second and the third number. So we always add the current digit of A and B plus the left shift digit from the previous multiplication or from the previous operation. And if we repeat this 3 times, then we get in the end here, with using the full adders at the right side, we are getting our result. And this is completely done in hardware. So we don't need any ALU logic, or we don't need any finite state machine, no operation or no coding, because we simply provide a 4-bit input A and a 4-bit input B, and then this circuit here in between will execute exactly the multiplication as shown at the bottom. And of course, you can scale this not only for 4-bit numbers, for 8-bit, for 16-bit, whatever. Then the matrix the scheme gets bigger. So you need more AND gates, you need more full adders, but the overall scheme is the same. So, and therefore you can also realize multiplication very, very fast if you provide a matrix like this. Okay. The next chapter is about our registers. I think for today it's enough. A lot of new details. So please make a repetition until the next week. You can skip the VHDL part and make a repetition of the remaining slides, that we can go ahead in the next week with our construction, okay? That's all for today. Thank you very much. And I wish you already a nice weekend, because we will not hear tomorrow, okay? Bye-bye.
Take care.
Tschüss. Dankeschön.